previously we talked about the graphene one, and there the most important information is always here. You have somewhere inverted band structure, and then on the boundary there will be a state metallic. And this simple assumption just there. And now here, let's talk about this, how to really identify this inversion quantitatively, and how to define the topological invariant. And since there, you must remember when we plot these topological surface states and just go from connection to valence, and this connectivity always there. And why important is this gap doesn't open. If it open gap, then it becomes something like this. You can push these states away. Then a symmetry really protect this state is time reversal symmetry, the time reversal. And this point, and then this indicates us like this topological invariant may be closely related with the time reversal symmetry. And this is true. And one way to define the topological invariant is like here. This is like, suppose this is the Bloch wave function. The chi is the momentum, alpha, beta, just the spin. And yeah, sometimes we don't talk exactly spin up and down because the coupling makes them. But we can see just the alpha and beta. And then this is the time reversal operator. And for a given Hamiltonian, we can always get this Bloch wave function, and then we get a matrix. And from this matrix, then there's a defined topological invariant. And simply, there, after the calculation of this, well, this just the matrix calculation, and we will not go to the detail, then the conclusion is simply like, if you get a number, this number is 1, it's topological insulator, is 0, it's a normal insulator. And here, you can easily get it. Is already, insulator can be classified into just two groups according to this method. Just two groups, either topological insulator or trivial one, then no third possibility. And why is how you see like -1 here, give you only two results, positive or minus. And then this is a general formula. If the system has a good symmetry, for example, inversion symmetry, this formula can be very much simplified. And we know if a system has inversion symmetry, then yeah, just a very simple case. One unit cell, this one unit cell. We have only one atom. Then if this wave function related with the s orbital, then we know here is the inversion center. We know this parity is positive, right? And if this is the unit cell box, if here this Bloch wave function is by some p orbital, whether x, y, z, you will have a minus parity. This is the parity. And then we know in a band structure, we have a band structure, we have many k points, gamma point, x and y. In a 2D case, suppose you have a cubic lattice, you have gamma, x, y, maybe here we call it m, but here x, y equivalent actually. And then for every state, we get a wave function, then we can define a kind of, like, for example, here, all positive or negative, parity over the valence band. But you may have many valence bands. Then just for each of them, count the parity. Then make a product of all these 4 points. Why these 4 points? Simply like, because these 4 points are the time reversal invariant points. Time reversal, we know time reversal for a general k point will becomes minus chi. We know for gamma, it will minus gamma, just gamma. X minus x, but they are different by 2 pi. And here is minus x. Yeah. Then the minus x, actually they are equivalent. Then here is time reversal invariant, here is same, here is same. But that's all, only these 4 points. There's no more. Then that means we count the parity of all the valence wave function at all these 4 points. Then make a product. If you get -1, it's a Ti. If you get +1, it's just a normal insulator. And then simply, we can understand from most simple case, why positive 1 means a trivial insulator. Like here, I mean this product, positive, means trivial. Oh, yeah.
Just a few detailed questions. So alpha B are spinor indices?
Spin, yeah.
And so the gamma I have the points, you were just describing the 4 points where there is
Yes.
inversion symmetry.
Yes.
So you evaluate this matrix at those 4 points.
Yes, yes, exactly. Yeah. If your system is 3D, then suppose this cubic case, gamma is here, x another corner, you have z, y in this corner, you will have 8 points.
Okay.
Yeah. Then do the same for the 8 points for all the valence bands. Yeah. And then you get a product. Most important here, you have 4 points. Here you have 8 points, but they are all even number. And then let's see why the product is positive means trivial. Total product means trivial is just normal insulator, and minus means the Ti. Why? Most simple case. Suppose we have an atom. For example, what atom? Like maybe this is the atom. We have a S and P level separate. A single atom like, well, we can put them, or they can be ordered in a lattice, but they are very far from each other. There's no hopping. Then there's no band structure. If you plot a band structure, just a flat band, flat everywhere. There's no dispersion. And then just means at all these points, they're same. Then they will give you the same parity, right? Then this same parity, whether this parity is positive or negative, then their product, you count 4 times or 8 times, you will get positive. Then that means one atom insulator is trivial. It's no surprise. Put one atom there, we don't expect some topological states come out, right? And then when we put this atom close and close, like they form a little dense lattice, then the band structure start have some dispersion. But if the dispersion is still very weak, we keep this gap not closed. And then it's still insulator. When you count the parity, they are still same for all these points. Only at a point, these bands cross and open, cross form a band inversion here, in this case. Okay, ready? There, this band structure, or this block. And, yeah. Yeah. Then you make the cross. Then the consequence would, yeah, let's see. The atom case, all the band flat everywhere. I better change the color. Valence and conduction, large gap, S and P orbital. And then they start to have some dispersion, but relatively weak. If the dispersion is strong enough, somehow actually they will touch. This touch just is a critical point. At the only single parameter there, you tune at this point, you tune away, it will go away. The gap will open again. Then you will get some band structure. This is the inverted band structure. We see it many times. And after the inversion, what's the consequence? At the beginning, everywhere is positive, negative, positive, negative. Now you have a positive here, negative here. Then let's think about like all these 4 or 8 points. What really happened is only at this one point, there is a gamma point. Only one point, you have a parity switch of 2 opposite bands. As long as this switch happens, this product will change the sign. And in simple, like this product just tell you whether there's some parity switch. And then your result will be either positive or negative. Now we believe in the atom case, the positive is trivial, then the negative is topological insulator. And good thing, well, here we assume we use the parity of the wave function to describe this, to define this topological number. And this called, well, because there are only 2 possibilities, right? 0 or 1, positive or negative. Then this is called a Z2 type topological invariant. And this mu0 is exactly this invariant. And let's see. Then here we argue the parity. We use the parity as an important property of the wave function. But here we assume we have inversion symmetry in the crystal structure. However, this is not always guaranteed in many material. One example is gallium arsenide or mercury telluride. And like silicon zinc blend, and this way has inversion symmetry because two atoms invert to each other. But now, gallium arsenide atom, there becomes two different atoms. There's no inversion symmetry anymore. And then we don't have well-defined parity. Then, well, we know the one way is we can still go to the original formula, just calculate this matrix. And, but technically, it's very hard. I would say so far it's not many people really use this method. And about this parity criteria is another very important consequences. If you have a system that don't have inversion symmetry, suppose we can just use the topological argument. You can deform it smoothly to another system. You have the symmetry. If you don't close the gap, fine. They have same topology. Then you count the parity of this inversion has inversion symmetry, this new Hamiltonian. And this also helps us a lot. And further, when we do this argument, you see, first gap closing, then open. That means we tune some parameter. For example, maybe whatever the parameter, maybe the strength of the smooth coupling. And well, in a real material, given material, you cannot tune it anymore. But suppose in theory, we just think in this way. And most importantly, there will be a critical point, band touch, and open again. This touching point, how it looks like, actually, it's a linear touching here. Will be a linear touching here. It's a Dirac crossing. Suppose, if we talk about a 3D material, and this is a three-dimensional band structure, then this touching will be a three-dimensional Dirac touching. Like graphene is 2D, you have Kx, Ky, they are linear. Now you have X, Y, Z, go to every direction, they are linear. And actually, it's a kind of three-dimensional Dirac point. This critical point. And then people also call, in this special case, is a three-dimensional Dirac semi-metal. And about this case, it lives only on this parameter. If you tune the parameter a little away, it will open gap, maybe a small gap, but it's not stable anymore. For Dirac semi-metal, and well, there are many different ways to realize a Dirac semi-metal, but obviously this is just one possibility. And okay, now we'll just keep repeating this band inversion picture. And this Dirac crossing is one way. Yeah.
I don't see here in white. If you have an even number of band inversions, then you don't find
even number.
Yeah, an even number.
Right. Then you don't have it. You have 2 minus. That means.
But you have some band inversions, and when you have a boundary, then with this game of connecting.
Oh yeah.
The bands.
You're right.
The same symmetry.
Yep. Very good question. Very good question. Let's think this way. This criteria tell you we need a minus. We need all the number of crossing. Maybe at the same point, all the number of band inversion, all at different points. Here once, another twice, and in total is odd number. And this only means like to guarantee you will have surface states. And but if we have 2, what will happen? And suppose, like just make it simple. Here we have one inversion. In a 2D case, here we have another inversion. Then each of them will give us the edge states. And like suppose we project it to a 1D system, and now in the 1D boundary, here you have surface states, you have another edge states, right? You have 2, just from this bulk boundary correspondence. We project it out, we get it. No problem? You can do it as the first step. Although when you count the parity there, you get a trivial number, right? Then the question comes from whether these two are robust. Like whether maybe if suppose there are some small impurity scattering between these 2 Dirac points, maybe it will get both of them. Yeah. And this question actually is super interesting. At the beginning, people just assume, okay, odd number, just super robust. But suppose if you have even number, then if you have additional symmetry, for example, crystal symmetry, maybe the symmetry can stabilize these two to avoid scattering between them. And this is exactly the case of topological crystalline insulator. For topological crystalline insulator, that material, I think maybe this is a famous one for crystalline insulator in telluride. There are like 6 times of band inversion in this 3D Brillouin zone. Z2 is trivial, not a topological insulator, but there are some mirror symmetry to protect them, make it very stable. And just when you do the projection, you get 6. Maybe in some case, they can 2-2 kill each other. And, but there's a mirror symmetry to avoid the scattering between them, then really stabilize it. And you get a topological state protected by crystal symmetry. But it's here, Ti is protected by time reversal. We will see time reversal is a little more robust, right? Here, crystal, you need some additional symmetry there. And later, I think this idea was generalized like to many, like not only mirror symmetry, maybe some rotation symmetry, or some even non-symmetrics glide symmetry and there. And then information is always like important is we have some inversion. Then let's say we project it out to the boundary. Whether it's robust, then it's another question. It's robust in the way whether it's kind of Z2 way relative to time reversal, or we need additional crystal symmetry. Okay. And yeah, later I will show you one example about like this even number of inversion. And is this picture clear? We know the even odd. Where it is. And yeah, I see a little about the parity. What is parity? And it's easy to understand here. If we, in this case, P and S orbital give you opposite parity, that only means in the unit cell here, we only consider suppose there's only one side, one atom there. If you have more, it will become a little complicated. For example, there are 2 S orbital here. Then the inversion center, maybe you can put inversion center here. You can also put inversion center in between. Then the parity change. Just depends on how do you choose the inversion center. And but this will not change your total result, because if you change at this point, the inversion center, you should use the same center for every point. And then in the total product will not change. The topology should not change because of you just change differential coordinate system. And that here also tell us something. 2s orbital. Ordinarily, we believe usually relative positive parity, but 2s orbital can give you -1. Similarly, 2p orbital, like this is s orbital, can give you either positive or negative example. This is the anti-bonding state. But 2p can give you also negative and positive examples. This is the bonding, this is the anti-bonding. The bonding simply means here they have more overlap in between, they form strong bonding. Otherwise, here they cancel each other, it's anti-bonding. It has high energy. And for PZ, it's very different. And that means when we think about atomic basis and the crystal structure, we really should put them together, put the crystal structure, identify the inversion center, and then we set the atomic orbital there. Then we can really identify the parity. And at the same time, when you put them together, you easily recognize which is bonding state, anti-bonding, then you know which energy is higher, which is lower. And then easily we can somehow plot the band structure by hand. You already get some feeling about the material. Okay. This is like a case. Like here, when we talk about this block wave function, it's already assumed that this is like a non-interacting system. this is all single particle Hamiltonian related to this wave function. And here, later people prove that even in the strong correlation case, and another topological number can be defined, and you can still, the topological insulator phase is still robust in the strong interaction case. But, well, I will not go to the detail here. And then here, this is just a simple summary about a TI, a 2D case. Suppose this is here the product at this point. And if you have 1 minus somewhere, you get a topological insulator. And for this 3D case, you have 1 minus or 3 minus. And however, this case, what will happen? Like we know we have a 2D TI, it has 2D edge states. We have 3D TI, it has surface states everywhere. But suppose we stack a 2D TI layer by layer into a 3D material. It really becomes 3D. What will happen? It will be a 3D topological insulator. Actually, not that simple. Just suppose let's stack them. And then let's first assume the interlayer coupling is very weak. Then that means when you're stacking, the band dispersion along z direction is very weak or relatively flat. Then that means in this gamma plane and z plane, actually the band structure are almost equivalent. Then your parity will be equivalent. And then you get 2 minus gamma and z. Then the total z2 is trivial, right? But this gamma and z, this 2 minus, also related to their question. And here, this 2 minus still makes something difference. And then therefore, there are, for 3D case, there are 3, this 0 is the mu 0 here, this mu. And then there are 3 small index to define the relate from the similar from the parity. And then this direction z01 simply tell you is stacked along the z01 direction. And here, people call it a 3D weak TI. And well, not a real TI. People believe it's weak just because there are 2 states here. They may scatter each other and cancel each other. And they might be weak. But later, people just realize weak TI is actually not that weak. And simple scattering cannot kill them. Actually, the only way to introduce strong scattering actually is to double the unit cell that overlap this one to this one. Then they overlap at the same momentum, they can open a gap. If you don't have such possibility, they just robust there. Then later I will show you the example. And then let's go to the material. And the first material, Mercury telluride, is the 2D topological insulator, was predicted in 2006. And yeah, I think this is the PhD work of Andre. And later, the second year, it was realized in Würzburg, in Molenkamp's group. And then Mercury telluride, as we already say, Mercury telluride, I said this because of strong relativistic effect, this s orbital contraction. This s orbital is very low in energy. It goes from the conduction band to the valence band, like compared to the light material, cadmium telluride. And this is the 2D case. And actually, here the band structure is for 3D material. And well, let's go to the detail later. And then another 3D family is the Bismuth telluride family. And they have 3D surface states. This is the result, experiment result from the photoemission. And now let's go to them one by one. And this is the band inversion of Mercury telluride. We're already familiar with it. Now, let's just recheck it from the viewpoint of band inversion and Z2. Yeah, it's good. We just compare a normal material, cadmium telluride, and mercury telluride. In the periodical table, they stay in the same column, but this one at the top position, mercury is at the bottom. Mercury is much heavier. And this one is not very different. This is the s orbital of the cadmium. This is the p orbital of the tellurium. This is clear, right? And for Mercury, because this S, its energy is much lower because of the contraction. And then it go to this position, inverted with here. Then, yeah, at the gamma point, what we usually plot is the gamma point. We still have this P band. This P band is still here. Just we have some S band here. And but go to the higher momentum. The S band is still here. And this is the firm energy. Then this one, just a normal semiconductor. This is semi-metal. The reason is here, the band degeneracy related with the cubic symmetry of the material. And here, clearly we see this band inversion. This inversion is happening exactly between this S state and here, the P state, and the red one. Although Mercury telluride has don't have inversion symmetry, but roughly we can argue, and this parity and this parity are different. Usually, actually, this P state form positive parity, and this one is negative parity. And we have a parity inversion. But important is the inversion happens between this S and this P. And then let's just guess if we have topological surface states, where the surface state will be. It will below it. Yeah. It will like just appear in the inverted gap. Here they inverted, then it like to appear here. Not necessary at the firm energy. Like actually when we use this argument, we don't care where the firm energy is. Maybe here, maybe there, it doesn't matter. As long as two sides are inverted. And here is same. As long as these two bands are inverted, between them, there should be some edge states, some surface states come out. And then the question, then here, from the Z2, we already know this inversion, they have opposite parity. For sure, it will give us a minus sign. And, well, right here. And then, but when we project on the surface, now we have a big problem because the bulk is metallic. Then later, your surface band structure may look like this. Your bulk will have a lot of subbands. Then you might have a surface this here. But here, you might see it. If you're lucky, you have a good resolution. But it just makes the bulk with the bulk a lot. Or even you see it, do you really believe it is topological surface there or not? In experiment, I see. And then one practical way, like, well, it's better if we open this gap, right? Then at least there will be some signal here in the gap. And there are many ways to open this gap. One way, since we argue this degeneracy related with the cubic symmetry of the 3D material, we just break this symmetry, like apply some strain and to make the ABC different. At least one of them is different from others. And we break the symmetry, we can get a small gap. And this was realized later. And the first proposal was like, oh, if 3D we have the problem, then let's go to 2D. If make this material as a quantum well, makes very thin film, like go to 5 nanometer or 10 nanometer there. Then in the 2D limit, the quantum confinement or finite size effect, just easily open the gap. Then you just get an insulator. Lucky thing is hope. What will happen with the quantum confinement here? Here, these states. Let's plot it larger. This is the P state. This is the S state here, maybe black. The S state here. P here, this is the energy. And then, because the electron, we know for the quantum confinement, and it's related with the thickness of the thin film, thickness D, and also related, well, how to write it, and the energy gap related also, the effective mass. of the particle. If you have an electron, we know the electron mass will be positive. If you have a hole, it's opposite, right? Then, because this band and this band, actually, this originally is an electron band. This originally is a hole band. If you apply quantum confinement, they will shift in energy in different way. And actually, this energy will go out. Suppose this is the thickness, D. This is the limit, almost 0, let's say that. And this will evolve in this way, where there are two states. Right. Then when in some window, here you see, oh, where's the red? There's some window you see. This is the ordinary order. Black is above, red is below. This is not a topological insulators. You just push it to the limit. And about here, you have a band inversion. And if you put the thickness in this region, you take out, calculate the thickness. Then this is exactly the prediction for given thickness, because the parameter for this material, all these parameters were well known at that time. People fit the band structure and get the effective mass. And even this kind of quantum well has been fabricated already for another purpose. Just nobody think about the topology at that time. And then the first theory proposed just propose, you make a thickness here. You confine your thickness here. Then you get an inverted band structure. But now your system, you have a 2D system. Actually, this one. You have a 2D plane. And then if you make a contact at the left and right, then your edge will be conducting. Since you have two states here, two states here, when you pass through the current, it will always only go through the edge. Then that means your conducting channel, one is here, another is here, to this direction. That's only two channels. Then your conductivity will be, conductance will be quantized, just to quantize the then the accurate prediction, this is shown, this prediction, let's say, if it's too thin, it's go to this limit. It's trivial. This is the calculation of the edge state. There's no edge state. If it's around 6.6, later experiment was done on 6.5, and then there will be edge states. And simply, this is the prediction, like in this way, if you tune the frame energy inside the gap, you measure the resistivity, the conductance, you get 0. And if you this one, you will get a quantized value. And then later, this is the experiment. Like experiment, in the very thin case, here the resistivity is super high. That means conductivity is almost 0. And here in this range, when the frame energy tune into the gap, this is the gating. And then there is almost the quantized conductance. And this is a direct evidence of these edge states. And simply from this cartoon, it's travel from two of these channels at both edges. And later, let's go to this material, 3D material, was further optimized to really like apply some strain to this 3D material and to break the symmetry. And this is our theory calculations, like really. Then later, what's the experiment observed? Actually, this is the photoemission one. And fortunately for this material, what's the photoemission? Photoemission just like you use a light to kick out one electron. Then you measure the momentum and the energy of the electron. Then you get the EK dependence. Then you will get just the band structure. And then that means when you kick the electron out, then you can only kick the occupied states out, right? If the states are empty, you have nothing to do. Then photoemission can only measure the occupied bands. And for this case, the frame energy actually is almost at this position. And there are some dispersion, you see it. And actually there's some dispersion in this way. And from theory, at this point is very close to frame energy, but actually below. And well, I would say without theory, it's harder really to believe it's related with topology. But here that is true. Later, these 2D surface states. Anyway, these two on the surface, it's just the two-dimensional surface states, even it's from topology. And it's two-dimensional. if the mobility is very good, and that means the sample is very clean, then you apply strong magnetic field. You do the quantum Hall measurement again, and you will get quantum Hall state. And that's not a surprise. Just means it's another 2D electron gas. Okay, then now we go to another more popular 3D topological insulator, and this family. And actually, this family material was known for many years. This is crystal structure. It's a little complicated, but let's say this is a layered material, and this is one layer. Like between layer, there are strong chemical bonding together, and in between this layer here is just one reverse interaction. They can be exfoliated, and inside every layer, you see this is the unit. It has ABC stacking in this way. And in the center, for example, bismuth telluride, here is selenium, both sides bismuth and selenium. And here, the selenium here, this atom, the yellow atom, is the inversion center. It has the inversion symmetry. And with like along this center, you can invert this one to this one, and this A to this material, this one. And this inversion symmetry will help us to understand the band structure next. And then this material, well, firstly, this material were like really known for many years. They are started as a very good thermoelectric material, especially bismuth telluride. How much time do you have? 1 hour? 1 hour, okay. Then let's first see, this is the ab initio band structure calculated, and looks some signature happens actually is here. And the gamma point looks like an inversion, but not, just from eyes. Well, we may guess there's some inversion even here. But when you exactly just count the parity, and then later you get all these three materials, they are topological insulator. And what will really happen is at the gamma point, exactly this picture. When you introduce metal coupling, they start to touch and then open a gap. And then this gap is a topological gap. Is here. Then let's go to, then the consequences on the surface, you have this metallic surface state. And then here, but for these three material, the detail, they are very different. But they have the same topology. And this one is the very light one. Like compare antimony is lighter than bismuth. Selenium is light than telluriide. And this is very light. That means its spelled coupling is weak. It's weak, then not enough to make this band inversion happen. And this is a negative example, but it's good for us to understand what happened. And then next, let's see the photoemission first. Well, photoemission fully agree with the calculation. For example, the bismuth. And this is another about the bismuth telluride. And then now let's go back to the material. Let's try to expand structure and what happened. Let's first start from one of them. The formula is bismuth 2, selenium 3. And the crystal structure, maybe we go later. This is the crystal structure. And we put a selenium here. Because it's periodic, I only plot part of it. This one, bismuth, selenium. This is only happens in one layer. And actually in one primitive unit cell, also include like just 2 bismuth and 3 selenium. Then let's think about its band structure, how it could look like. Actually, bismuth, in the atomic level, it has its 6p or 5p orbital.